Good afternoon. Thanks for coming to the after coffee break presentation. I'm presenting an approach for the assessment of microservice architecture deployment alternatives by automated performance testing. So the idea is analysis of microservice DevOps application. And the outline is, first I'm going to talk about who did this, how you approach the development of this research, which is a very important part of the result, is the people that are involved in the research. Then I'll give you a background on load testing, analysis of software architectures, some related work, and then step 4 is going to be the approach for scalability assessment of architecture alternatives with examples. So basically, it's interesting that in the morning people talk about landmark and topology maps. And our team is globally distributed, and some decided to represent themselves in maps, others in landmarks, right? So we have here Professor Andrea van Horn from Stuttgart, and he put a map of Germany, only Germany and the German-speaking countries around. So that's his view of the world, right? And then we have Barbara and Andrea from Bolzano University in North Italy, and they added a similar view of the world, but now North Italy is there and other German-speaking places, but South Italy is still nowhere to be seen. My company, Lab Solutions, is close to Princeton University, so I put a landmark, Princeton University. This is the rector of Princeton, Nassau Hall. This is a very historic building that was the seat of the US Congress during the War of Independence, and there are some bullets there that the British made during the war still. And I am there in a selfie, and behind me is one of the co-authors, Vincenzo Fermi. Right? And that picture was a selfie I took at Performance Engineering Conference, right? And from Novatech, we have Henning Schultz, that he's in Karlsruhe, right? So you have a globally distributed team working together. And here you have the name of the companies. You have University of Stuttgart, Novatech. You have Università Svizzera Italiana, Lab Solutions, that's me. And a quiz for you, who can read my logo, understand what's in there. and I tell you, it means scalability. And the question is, which language is that, right? Then you have University of Bolzano, Barbara Russo and Andrea Janes, and you have several other collaborations from SPEC Research Group. So basically, we talk about DevOps this morning, right? What is DevOps, right? DevOps is continuous software engineering, which is a set of really good practices, and the objective is to reduce the time between committing a change to a system and the change being deployed in normal production while ensuring high quality. So what are the key practices? We have online monitoring, microservice, continuous development, cultural change, agile, automation, Docker, lots of good stuff. But how do you put all of this together for automated performance testing? And how do you know you have good quality, right? How do you analyze elasticity, security, reliability, all these great characteristics, right? So what I'm trying to do here is to see what's the balance, how we can balance. We want to integrate established quality assurance with DevOps practices, and how can we develop, well, can we support quality assurance with this, right? So there is a trade-off. You cannot do everything. So talk a little bit about what load testing is. So what's the objective of load testing? What you're trying to do? You are trying to assess the behavior of a system under load with the objective of detecting load-related problems, right? Usually you have a workload specification, you have a driver, a system under test, and a performance monitoring, and you have nice curves that you can plot, workload versus throughput. But many places don't do this anymore, and that's what you get, temporarily not available, right? So you go to a website, and sometimes it's great, sometimes it's not. And people may have missed some of the key parts. You have to have your usage profile, You have to make sure your program is correct. You have to have a good architecture. You have to analyze all kinds of deployments and many other things. For example, requirements engineering, all kinds of other activities that are required to get a really good, high-performance, scalable system, right? So the classic load testing approach is that you have an expert, a guy that knows everything, and high manual effort for maintaining load testing, right? That's a problem that you have. Then there is some system under test, and test takes a long time to execute, right? That's another problem. Then you have very complex analysis of the results for regression. And usually they are not suitable tests. So this is classically used to take very long time and it's hard to maintain, right? So classic, it's a hard problem. And now you put all of this integrated in a continuous development pipeline. So hard problems become even worse, right? Not only you have high manual efforts, but you need to automate everything. And load test takes lots of time, but you need to have frequent and fast releases. How do you deploy this on top of very fast releases, right? Complex load tests for every release is very difficult to analyze and do regression if you are having lots of builds per day and have to analyze all the results all the time, right? And service focus requires lots of tests, right? And you don't have that, right? So what do you do? So there is this German government-funded project called Continuity IT project between Novatech and University of Stuttgart. The vision there is to go into full automation, automated extraction and evolution of tests, modularization and semantification of load tests, detection of performance regressions, and automated diagnosis. So the vision is you need to automate a lot of this stuff, right? And this is some related work, how to do automated extraction. And the main vision is we integrate everything into a pipeline and have lots of tools that do your workload model evolution, your selection of workloads, your automated execution, regression detection, regression analysis. So several tools that are developed by Novatech and by University of Stuttgart to do this, right? And also you have issues in managing required minor changes. So now I'm going to go into the method that we are presenting in this paper for scalability assessment of architectural alternatives using load testing. So the real challenge here is to assess performance of architectural deployment alternatives, right? You have Docker, you have lots of deployments, and how many replicas you're going to do for every component, what's your CPU memory allocation, like how you're going to develop your technology stack, and under completely fuzzy requirements. Requirements are not well defined, right? So how do you analyze this automatically and come up with a metric that people can understand if your system is good or not in terms of scalability, in terms of security, in terms of survivability, and other metrics, right? So our approach is first to use the operational data to generate and weight load tests. We want to measure baseline requirements. So one of the key roadblocks for good performance testing that when you are in a project and you ask for performance requirements, usually people run away from you. Nobody wants to talk to you anymore. No friends at coffee break, right? So it's a really tough. Nobody wants to commit to performance requirements. So what we decided to do is to automatically measure the performance requirement from the system that was deployed. And then you have a metric that allows for quantitative comparison of deployment alternatives. And we build on previous work that we did for telecommunication systems about over 20 years ago. We had this problem about load testing on AT&T switch. And what we saw that you could partition the load into states. And the states represent a snapshot of a system at current time. So basically, for the telecommunication switch was the number of calls of each type that were in execution at time t. And we were able to build Markov chains, to do state profile, and to generate efficient load tests and get really efficient domain-based reliability assessment based on this approach. So what you are doing now in this paper, we are generalizing that concept that the load could be partitioned to states. So basically, the overview, this, if you understand this picture, this is the key of the presentation, right? You have a system in production, and this system has some load. You have some observed load situations, and you analyze the load situations, and you have a frequency distribution of your load. So basically, you are saying you're applying partition testing to load, saying that each load level represents a unique state in your system, and that you validate that that state is correct. All the other situations with the same load will have similar performance in terms of resource usage and so forth, right? And from that, you generate sample load tests. And from the sample load tests, what you have first is a baseline test that you run with no load, and you compute the average response time and the standard deviation for the no load situation. Then you define a scalability criteria that says my scalability criteria is going to be average plus 3 standard deviations. So you can automatically measure the baseline requirement and run tests for several different deployment configurations. For each of those tests, you can have a pass-fail criteria, right? And you apply this to a microservice architecture. The SOC Shop is an open source tool that you use, right? And then you generate a domain metric where 1 is perfect and 0 is no good. So how you do, you just do, I have a state, I have a probability of being in that state, and I have a reward that I assign to each of those states based on the results of the test. And what I do, we measure for every single microservice what is a pass-fail criteria for certain load and for certain deployment configuration, and you are able to very simply compute this domain metric. So we ran several experiments here. We had 12 microservices in production, 6 load levels. In terms of the state is number of concurrent user sessions, and we look at 10 configurations in terms of memory, CPU, and deployment, and our scalability requirement was average plus 3 standard deviations. So what we got is, if you look at the state distribution, for 50 users have 0.1058 probability of occurrence, and the interesting one, 250, 0.20370, right? So this was the max probability of occurrence. And for each, this is the maximum contribution to the domain metric without the test for this configuration and certain deployment paths, right? And when you run the tests, these tests are going to all these microservices, and I know for each of those tests what's the percentage of activation of the microservice and what's the pass-fail criteria. So the measurements tell me how much probability mass I lost because of failed tests. And what you see that for this test, the maximum was 0.20370, but the actual measure for that configuration was 0.135 because of failed tests. So for the whole deployment configuration that we have for all the tests, the maximum will be 1, and the actual was 0.77. And if you look at one, this is the most interesting result that you have, because whenever you go to cloud, to Amazon or to other places, and you ask them how much CPU, how much memory, how many instances, they say, oh, add as much as you can. No problem. I send you the bill at the end of the month, and then your accounting guys start calling you, right? But what we saw here, that for 1 gigabyte 0.25 CPU, one replica, you had a metric of 0.77631. But for the same configuration, 4 replicas, then it was a significant degradation in performance, right? 0.3162. And in fact, the best metric was not for the largest configuration, right? You have configurations with more memory, and you have degradation in performance because of more duplications. And for this system, the situation was that the bottleneck was in the database. So if you add more instance or more CPU or more memory, you're just increasing the queue in database, and that did not help you, right? So you had a degradation in performance by adding more resources. And the main conclusion of this evaluation, that careful performance engineering is still a requirement. The fact that you have access to lots of resources doesn't mean you just have to throw resources. You have to understand what are the bottlenecks of the system. You have to have a way of measuring that, and you have to optimize your system accordingly, right? And you had two measurements. One was for a very large high-performance infrastructure at Stuttgart University, and the other was for domain metrics based on virtual machines. So we have our Mercedes-Benz and our Fiat here. In Italy, we had little machines, and in Germany, you have very large, very fast machines, and you see how it impacted the metrics. So this is very nice to be able to see the impact of the power of the computers and of the configuration visually, right? And what we envision to do is to have this visual representation where this top curve shows what's the maximum that you can achieve for each load level. So for example, if I have 50, is 0.10582, what I had in the table before, right? If I have like 250 was 0.237. But because of failed tests for certain deployments configuration, you see a degradation, right, in performance. So there is a loss in the metric because of failed tests for different deployment configurations. So by looking at this, you can immediately see that different deployments have different benefits depending on the probability of occurrence, on the number of tests, right? You can visually see the impact. Wrapping up, so load testing, continuous delivery pipelines makes existing problems worse, right? You need to have an automated approach to relieve those issues, right? The vision is to have lots of automation, lots of tools to be able to do this, and you need to have first an idea of how your system is used in the field. You have to have a usage profile. From this user profile, you can have a state probability distribution, and you can generate a domain metric that could be easily shown to customers in terms of scalability and other metrics that you like to have, right? So as future research, like there are lots of additional efforts in load testing and in microservice and continuous software engineering, but one of the most interesting future areas is to apply this approach to other quality attributes. You like to be able to look at security, at survivability, and other metrics where you can correlate the non-functional performance with the performance of the system, with the timings, right? And you're always interested in technology transfer, so anybody wants to have case studies and apply, come talk to me afterwards, right? And here we have a few readings that you can do.
Or just like at home. Right.